In part one, yesterday, we saw a bunch of techniques based on this idea of sketching large amounts of data. Primarily, yesterday, we looked at data represented by a large vector. And we said, actually, there are very space-efficient and relatively efficient to construct summaries of those vectors that allow us to do things like testing the equality between two large vectors, recovering entries approximately from those entries with additive error, approximating the Euclidean norm, so getting a Johnson-Lindstrauss star result, and also dot product, approximating the number of non-zero entries, F0 or distinct elements problem, and approximating set membership, so sort of approximately encoding binary vectors. So what we're going to do today is sort of start making more use of these kind of ideas, building more structure on top of them for more advanced computations. So it's a little bit of a scattershot approach. I'm just going to sort of pick up a few topics that are currently in vogue, currently having activity around them, but still with a lot of potential to do more work on there. So we're going to start by sort of looking at sampling, but sampling primarily through the lens of sketching. We're going to look at sort of particularly this notion of LP sampling, where we want to sample proportional to the fraction of the LP norm that an element represents. Use that in two ways. Use the L0 sampling to give us some traction around graphs. Use L2 sampling as a different way to look at the frequency moments that we started looking at yesterday. I'll talk a little bit about matrix computations. This might be somewhat compressed because it sort of echoes, but from a slightly different perspective, what we already saw on Wednesday about matrix computations. And I'll try also and talk something about lower bounds. Again, these are lower bounds that came out of communication complexity, have been applied to streaming, and also apply to this idea of sketching. So these actually tell us what's the smallest that our sketch summary can possibly be for a variety of problems. And it's also nice computationally because it sort of brings us back to the idea of reductions between problems. And you put a lot of effort into proving one problem hard, but then that gives you a lot of power because you can then show a lot of other problems hard by reduction. So I talked about sampling. Let's actually just firstly think about sampling over a large amount of data. It turns out that that's not a completely trivial problem. Suppose I have a large amount of data, and I want to sample some small number of items, say small m items, uniformly from this data. So this is, in principle, this should be straightforward, but this can be challenging if we don't really know how large that total input is going to be. Think about the case where our input is sort of continually arriving, so we're seeing more information. That input may be sort of split over different locations. So actually, we can't just immediately work out what sampling probability we want. In some way, we want to sort of adaptively sample. So we want to draw something that looks like a uniform sample of what we've seen so far, but also be able to sort of modify that sampling process as the scale of the data increases. So in fact, this is sort of fun because when sort of restricted to that streaming setting where you just see items arriving, this has almost become a cliche among sort of technical interviews at Silicon Valley firms in the form of reservoir sampling. So I'm actually going to show a slight variant on sort of the solution there, because I think it's just a very neat idea that's actually quite addresses itself to nice kinds of analysis. So I'm going to do the following. I'm going to come up with a random sampling process based on sort of a random tagging idea. So for every element that I want to have a chance of including in my sample, I'm going to associate that with some randomly chosen value. Think of it as just some fraction between 0 and 1. And my sample is going to consist of the items with the smallest values of this random tag. So if I want a sample of size m, then I'm just going to pick the m smallest random tags. So already this seems a little bit reminiscent of the k-minimum values algorithm we saw yesterday for F0. So the difference there is we're using a hash function to generate these tags so that when we saw duplicate items, we made the same sampling decision. Effectively, we're doing something very similar here, but we're making independent sampling decisions. So we're sort of sampling from the multi-set rather than sampling from the support set. Right, so here's just a toy example. We see some item. We want to sample just a single item. we associate a random value with it. That's obviously the smallest we've seen so far. See another item, another random value, that's bigger, so we don't pick that. Another item that's smaller, so now this becomes our single sampled item, and so on. So, why is this the right thing to do? It's just a very sort of easy symmetry argument that says, well, because in this case, because we're choosing these tags sort of independently of the items, then every item has the same chance of being associated with the smallest tag, so it's completely uniform everywhere. All sort of samples are equally likely. Why is this nice? It's nice just because it sort of completely separates out this sampling process. It makes it easy to analyze. It sort of fits into this model of distributed computation and mergeability because independently, I can run this on my subset of the data, you can run this on your subset of the data, and we can just merge our samples and pick the items with smallest tags amongst those, and immediately argue that, well, this is exactly what we would have got if we just deferred that sampling decision to looking at all the data together in aggregate. And I'll just very briefly, unfortunately I don't really have any time to talk in any depth about computational geometry, but this sort of gives you a foothold into computational geometry just because the first attempts at building epsilon approximations, that is sort of a summary of points so that any range query in bounded VC dimension over those points you can answer with sort of small error. The first approach to building epsilon approximation is just to build a sample of sufficient size. So again, this sort of is your doorway into computational geometry on big data.
It's essentially the same as the mth item is, of course this requires counting. The
Yeah.
mth item is selected with probability.
Exactly. Yeah. So it's exactly isomorphic to. So the comment is just that this is pretty much isomorphic to the idea that, which is sort of what people sometimes refer to as reservoir sampling, where if you're seeing a sequence of items, you pick the mth item with probability proportional to 1 over m. For some cases, just I find this sort of view of the world slightly easier because it sort of decouples you from that sequential view of things. Okay, so that's how we would sort of start by sampling, but let's sort of look at a slightly different kind of sampling problem, where we want to achieve a different sampling distribution. So now we're in a slightly more general case where we're seeing inputs that are describing frequency vectors again, where those vectors can have entries where some entries are positive, some entries are negative. We want to sample based on the overall frequency distribution. What are the kind of sampling tasks we might want to do? We might want to sample from the support set of those items. So again, just associate the same uniform sampling probability for every item that has a non-zero frequency, but not sample from the items that have 0 frequency. We might want to sample proportional to the absolute weights of the items in that input. We might want to sample proportional to some function of the weights. So there's a set of techniques that have emerged recently that are now referred to as LP sampling that collectively address these kind of questions. So in particular, they say, well, let's generally look at the class of sampling distributions where we want to sample element I from our distribution with probability ideally proportional to element I's contribution to the pth power of the p norm. Okay. So p here is our variable. That's why it's LP sampling. Fi is the frequency of the ith item. So L1 sampling just says essentially sample proportional to the absolute weight of the item over the sum of the absolute weights. L0 sampling gets us this notion of sampling from the support set. L2 sampling says sample proportional to the square of the item weight over the sum of the squares, and that was alluded to in the matrix computation talk as being a sampling distribution that works well for sampling rows and columns for a variety of matrix products and other computations. So again, because we're in this sort of small space setting where we're trying to do this based on compact summaries of the full data, we're not going to be able to sample exactly from this distribution. We're going to, again, tolerate some small relative error in these sampling probabilities. And over the last couple of years, we've seen solutions arising that are efficient in the sense that we can draw one sample based on a summary whose size scales proportional to 1 over epsilon squared polylog. I say efficient because, again, I sort of, as I said yesterday, we tend not to worry too much about the constants inside this big O notation, but these constants are sort of currently large enough that they make it a little bit off-putting to do this at scale, but it suggests that this is still within the general realms of practicality. And why are these constructions interesting? As I've alluded to already, L0 sampling we're going to use to look at graphs, and L2 sampling we're going to use to look at frequency moments. So these two approaches actually need slightly different constructions. L0, being the zero pseudo norm, is always somewhat difficult to handle. So we'll do that first, and then look at the L2 case. So L0 sampling, we want to sample from the support set. Why is this difficult? It's difficult in this particular case because I'm looking at inputs with positive and negative weights. So in particular, if I just start sampling from things that appear in the input stream directly, then it's entirely possible that I'll have a somewhat difficult arrival distribution that sort of zeroes out their contribution later, right? So I can definitely think of inputs where I see a large number of items present somewhere in the input, but in aggregate at the end there's only a small number of items with non-zero frequencies associated with them. And in fact the construction that we're going to see for graph sampling really makes very critical use of that. So we really need to be able to handle the fact that we're dealing with varying weights of items, and so we want something that's more in the realm of this sketch summary that we can think of as a linear transform of the input, because essentially as soon as we're in that realm of linear transforms of the input, then everything sort of works fairly neatly. We don't have to worry too much about arrivals and departures explicitly. They're just captured by that transformation. So we want to look at this idea of L0 sampling. We want to be able to sample approximately proportional to, approximately uniformly those items that are present with non-zero frequency after we've seen our input. So there's a relatively, there's basically been quite a lot of work on this, but when you step back from it, there's sort of a single template, a couple of ideas chained together that really make this work. They rely sort of at the heart on the idea of sparse recovery. They rely on the fact that we know lots of constructions that say, well, if I have a vector that's relatively sparse and sort of truly sparse, so now I'm talking about a vector that has, say, k non-zero entries and everything else is zero, for some small k with cost proportional to k, I can basically recover that vector exactly. Okay. So I'm going to use that tool at the heart of this. I'm going to say I can recover sparse vectors exactly. I can exactly reconstruct that. Well, that would actually be what we need if we were only interested in sparse vectors, right? If I see lots of arrivals and departures of items, and at the end I have a sparse vector, then I can just have fed all of that into k-sparse recovery structure, sketched just that remaining vector at the end, recover that, and then directly do this sampling from that vector. But obviously I don't always have that situation. Quite often I have a much denser vector. So what I want to do is say, well, all right, well, let's just make things sparse. Let's essentially subsample from my input. Let me sparsify my input so that I have sort of sampled down to a sparse vector, recover that sparse vector, and then sample from that. Then the question is, well, how do I know at what rate to subsample from my input, right? I might end up with a case that my input is very dense, so I need a very selective sampling process. I might end up with a case that my input ends up only moderately dense, so I need a relatively high sampling probability. How do I choose? Well, I'm a computer scientist, I don't have to choose. I'm just going to make a bunch of guesses in parallel and argue that one of them is going to succeed. So in particular, what I'm going to do is just look at a geometrical sequence of sampling probabilities. So I'm going to start with my input. I'm going to look at my input once sampled with probability 1. So think of this sampling process as basically giving me a mask over the indices of this vector. So when I sample with probability p over this vector, it's as if I'm masking out a 1 minus p fraction of the entries in this vector and just ignoring them, treating them as if they're 0, and only looking at what gets through that mask. So at probability 1, I'm just sampling all the indices in my vector and feeding that into an instance of a k-sparse recovery algorithm. With probability half, I'm sort of passing half of the indices into a k-sparse recovery algorithm, probability a quarter, an eighth down to some very fine sampling probability. So this is going to work out if there's some level where that sampling probability is small enough that I get a vector with at most k non-zeros in it, but not so small that that vector is a 0 vector, right? So that's the only game I'm playing. I'm just playing the game by saying, I want to argue that I can sample fine enough that I get something that's going to fit into my recovery structure, but not so fine that I actually lose everything. So that turns into just a relatively simple argument. Basically, because we're doing this sort of geometrically, we're going to pick a k that's large enough so that probably we're going to find some level where we have a constant fraction of k items passing through, and that's the level that we're going to actually do this recovery at. So to say that more formally, we know just because of this doubling process, there's got to be some level where the number of items that pass this sampling filter is between, say, k over 3 and 2k over 3. So we're sort of somewhere in the middle of this distribution. And our bad event is just if, so this is our expectation. Our bad event is just if at that level we end up too many, so we end up more than k, or too few, we end up less than 1. Right? So this is just going to be another Chernoff bound kind of application that says we should be sort of comfortably in this middle zone. The only reason we're going to go too far to the right or too far to the left is if an unusually large number of bad events happen. So through the Chernoff bound, we're just going to argue that this picking k large enough, we're going to be close enough to the expectation that we don't have to worry. Okay. So what this says is, yeah.
I might have missed this, but
sure.
How do you know k a priori?
So k is actually a parameter that we're choosing. So we're choosing k here. This is part of our construction. We're going to choose k, and our cost is going to depend on k, so that enough things pass with high probability. So this is actually how we're picking k. We're just picking k, in this case, proportional to log 1 over delta, to say we're going to be sort of within between k over 3 and 2k over 3
just a fair
things.
probability that it's nothing else hidden in there.
Yes.
I was wondering if there was anything else hidden in the k selection. Just log 1 over delta, basically.
Here, yes, yeah. It does actually crop up again slightly later, but it turns out that log 1 over delta is sufficient for that use as well.
What does it mean to pick level p? Because you don't know n.
So for this analysis, I'm going to pretend we do know n, because n is the number of non-zero things. So it's just in parallel, you can do an F0 estimation to tell you what level. Again, in practice, what you can do is actually just be greedy and just say, well, this k-sparse recovery algorithm, I'm going to talk a little bit more about how this works. But basically, this algorithm is either going to say it's a 0 vector, it's going to say it's a k-sparse vector, and here it is because I can recover it, or it's going to say, fail, this has density more than k. So what you can just do is just sort of go through these repetitions and pick the first one that succeeds. That biases you slightly, but in practice it doesn't really change anything. Okay. So this gets us to the point where we're kind of reliant on this k-sparse recovery data structure in the middle. How do we actually build such a structure? To some extent, maybe we can just sort of pass off the problem and say, well, this is actually the core problem at the heart of compressed sensing sparse recovery. This is a solved problem. Just for the sake of completeness, I want to argue that we already have enough tools to get us something that works pretty well here. So a first approach to sparse recovery is to use one of the sketches we saw yesterday, count-min sketch. Because our input is a sparse vector, what we can do is just sort of go through that sketch, query the estimate for every item, use the analysis of the sketch to say that basically 0 items are most likely to still look 0 when viewed through the lens of the sketch. Non-zero items will actually be recovered. So that sketch is going to work fine. It's just that it's rather slow because we're sort of iterating over this universe. The universe we're assuming is massive, so we don't really want to materialize that. So essentially we have a structure that gives us an oracle to ask element frequencies, but we want a faster way of interrogating that. So here's sort of one of the tricks that people have used. It's a nice trick, so it's worth sort of looking at. What we can do, we have our sketch. Our sketch is sort of mapping information about items. We're now sort of in the setting that we're interested in the case where the vector is sparse. So yesterday we sort of analyzed this sketch and argued what's the pollution of our estimate based on colliding items. Here we're sort of going to build a sketch that is sufficiently large. We're not going to have much pollution from colliding items. What this is really doing is just doing a random mapping of items, and we can recover an item from this sketch if it doesn't collide with anything else. Right. So we're sort of taking items, mapping them into a sketch structure by a hash function. Things are so mapping down to a small range, but that range is just large enough that there's going to be some cases where there aren't collisions. So all we want to know is sort of look into a cell in our sketch and determine when is there a single non-colliding item within the sketch. So what we can do is before within the cell for a sketch, we kept information just about the total mass of elements colliding here. What we'll do is we'll keep essentially that information about the mass, but we'll also keep this what we call sum information, where we think of this as the sum of the item identifiers.
Graham,
yes.
Can you not make that first approach better by using the heavy hitters technique you talked about yesterday?
You can. So the heavy hitters technique I talked about yesterday, that was a relatively straightforward technique that did the sort of a dyadic range binary tree divide and conquer approach. In this case, I've changed the game a little bit. That worked when you had a vector whose entries were non-negative. You could do that divide and conquer approach, and you're nodding because I think you've got it, but let me just sort of complete the argument. When they're all positives, you can kind of discard a branch of your search tree when that search tree branch looks light, because you can be sure there's nothing heavy within a light branch. When you have both positive and negative weights, you can have something where the sum of those weights looks light, but it's because there's a heavy positive and a heavy negative in there. So there are actually some more sort of coding theory tricks that let you build other ways of doing this search, but because we're in a slightly simpler case here looking at a sparse vector, we can do these kind of tricks. So what we're going to do here is keep information about the sum of the item identifiers that hash into an entry, as well as the sum of the weights of those items. So imagine that you have, item 5 occurs 4 times and is mapped into a cell on its own. Then we'd have the sum of the item identifiers being 20, the sum of the weights being 4, so we can just divide that sum by the count to get the item ID, right? If you have 5 copies of item 4, 20 over 4 gives you the item 5 ID back out of that. So that's obviously going to work if you have a single item in a cell, but what you have to worry about is what if you have multiple items colliding in the same cell. Are you going to get false positives? where it looks like there's something there. But for simplicity, what we can do is just say, well, let's actually keep also a fingerprint of the kind that we talked about yesterday of the vector of items that hash into that cell, and then use that fingerprint to check, well, if I recover an item from that cell based on some account information, does the fingerprint agree with that sort of one sparse vector that I recover? So what this is really doing is saying, take the k-sparse recovery problem, hash to a moderate width domain, and then perform one sparse recovery within each cell. And you can sort of plug that all together and argue that actually this k-sparse sketch is relatively compact k log u. So it's kind of comparable to the k log, or the I forget the terminology, it's s log d over s that we saw for sparse recovery. And again, you know, just a question of how much you want to drive down that log factor. Okay, so just sort of stepping back a moment, what does that say? It says we have the sampling process. It says that we can construct either using sort of sketching ideas or other techniques, something that will do the sparse recovery. We plug that together, we sort of pick the right level to recover at, we do that recovery, and that gives us something which we want to argue is a uniform sample from the set of items with non-zero frequencies. There's a slight argument that I'm not going to go in that sort of says, well, we actually have to worry a little bit about the uniformity of this process. Because we have a failure probability, we have some small probability that we're going to have too many items at a level where we should be able to recover. This is going to slightly bias us. But you know, even in the worst case, essentially that only adds a failure probability delta to the recovery probability. So it sort of just merges our parameters. It says if we want to give that sort of one plus or minus epsilon probability of uniformity, we just have to pick delta around epsilon, and we're all good. Okay. What that argument says is that we can construct this kind of L0 sampling process. So let's actually make use of it. Let's use it to learn something about graphs. This is due to Kuchinan, Sudipto Guha, and Andrew McGregor. Let's think about a very large graph, which again we're viewing in this sort of streaming world where we're seeing edges arriving and departing. I want to say, can we make some sketch, some linear transformation, essentially a linear transformation of the adjacency matrix, so that after we've seen all this information, just using those sketches, we can determine connectivity properties of this graph. So it's an undirected graph. Connectivity, we want to test if there's a path between all pairs. In fact, what we're going to do is we're going to recover the connected components. So what would we do, you know, just in a sort of algorithm setting without any of these space constraints? A relatively natural and quite parallel algorithm for connectivity, finding connected components, is just to say, well, start with every node in its own component, and then start merging components where we see edges connecting components. So look at the current set of components that we know about, identify if there are some edges between components, contract those edges, and merge those components. What we're going to do is use L0 sampling to help us find edges between components that we can contract. So sort of when you first look at this problem, it looks as if it starts working and it looks as if it's not going to stop working, right? So if I think about taking that approach, take each node in the graph, use the L0 sampling structure to let me sample uniformly from the set of edges instant on that node, then certainly straight away I'll find an edge instant on this node, be able to contract it, an edge instant on this node, be able to contract it. But if I think about sort of iterating this procedure as my components grow, I sort of hit a problem. The problem is that as these components grow, if I'm sampling uniformly from the set of edges instant on a node, then it seems I'm most likely going to learn about edges that are internal to a component. What I want to do is I want to, in some sense, ignore internal links within a component because those don't tell me anything new, and only focus on edges that connect across components. So it turns out we can actually do that using a clever encoding of the edge adjacency information in such a way that we can merge the sketches of all nodes within the same component and end up with a sketch of the component adjacency where the internal edges disappear and the sketch is now summarizing only the outgoing edges. So essentially it relies on the fact that using the sketching technique we can encode both positive and negative weights, and we can encode those positives and negatives so that when we add up sketches, an internal edge has a positive component from one node, a negative component from another node that exactly add up and cancel out. So the way this works is think about this. We have the edge ij linking node I to node j. Enforce an ordering on the nodes, so we're going to encode this edge in two different ways. For node I, canonically think of I as being the node less than j, we're going to encode this edge positively within the L0 sample sketch for node I. So think of sort of the single unit ij representing the edge being associated with the node I. And we're going to also encode that edge negatively for the partner node where the node j is greater in the ordering. And this has that property that I talked about, that if we think of I and j being in the same component, we're going to sum their sketches. So that basically means aggregating the set of items associated with them. So we have the item ij with weight +1 associated with node I, the same item ij associated with -1 for node j. So when we add those sketches, we're sort of adding those contributions. And now that the item ij has weight 0 in the sketch, and so it's no longer represented. It exactly cancels out, and it sort of goes through that whole data structure through to the K-sparse recovery structure and sort of cancels out there. So what it means is if you look over a component being formed by a collection of nodes where we've summed the sketches associated with those nodes, then all the internal edges have precisely cancelled out, and we're left only with the outgoing edges represented in the sketch. So then when we recover from the sketch, we can sample from the outgoing edges and identify more edges to contract to further collapse the components. There's a little bit of care needed in the analysis because essentially one has to be very careful when recycling randomness. Right? We can't really argue that you can reuse the same sketch in exactly the same form in too many ways. Quick question.
Hi.
Yeah.
So do you know for a fact that you need the independent randomness? I couldn't, I don't know how to prove it without that.
Yes.
Do you know, have you come up with any family which you can show requires the independence?
Well, so I don't know if I can give the strongest answer. So the question is how much do we need randomness across sketches, because we're going to sort of interrogate them multiply. So I don't know the strongest answer to that, but here's sort of the thought experiment that I usually use for sort of pushing us in that direction, which is, it's very tempting to look at just a single L0 sketch in this setting and say, well, I can sample an element from that sketch. Right? So in principle, what I could do is take that element that I sampled from the sketch and apply it as a negative update back to the sketch to kind of cancel out that item, and then say, okay, I've just done a linear update to my sketch that's removed this item. Let me sample from the sketch again and get something else, and then take that out and sample again and get something else. And it's clear that that shouldn't work, right? And why is that? It's because the analysis of the sketch that says you should succeed, you should be able to sample something, is sort of conditioned on the randomness. And what you're doing, if you're sort of feeding things back into the sketch based on what you draw out, is you're, in some sense, conditioning on what you've drawn out. So we know that for a compact sketch, there shouldn't be some way of sort of just somehow unraveling and pulling out everything that it summarized. And that argument, and that breaks down because of a lack of independence. So that sort of says that we must,
I have that intuition too, but you haven't come up with, I have never been able to formulate that as to envision a counterexample.
Okay.
But you haven't either, I said.
Between sampling with replacement
So it's what it's really asking about is the way we're going to use sketches in this way is we're going to sort of argue, we're going to actually do several phases of sampling, and for the analysis that we know that works, we're going to argue that actually we're going to use fresh sketches for each step, because we're sort of concerned about reusing the same sketches and not being able to make independence arguments across them. And what Valerie is asking is, well, do we know for a fact that we absolutely need to do that? In this case, it's maybe not terrible, because it basically incurs as a log factor. But ultimately, we want to know whether that's the case. And I think I'll defer to Andrew to take this question offline and answer it later. But yeah, very interesting question, and very, very pertinent exactly to this. The way we know how to use this is to say, well, we want to be a bit cautious about going back to the same sketch at every step. So let's essentially in parallel sample an edge instant on each node, collapse, then think about sampling an edge instant on each component, collapse and repeat. If we have a fresh sketch for each step of that process, fresh sketch in the sense that we created all of these in advance in parallel, so we're not actually going back to the data, but we're just sort of starting with the sketches, sort of the first set of sketches, using them to generate the first set of components, then building a sketch of those, using the sketches of the nodes to come up with the sketches of those components for the next round, and so on. Then how many sketches do we need? It's sort of relatively obvious that we're going to collapse a constant fraction of components every round in expectation, so with high probability we're going to need a logarithmic number of rounds, so we only need to sort of pre-prepare a logarithmic number of sketches, and the question is, do we actually even need that many? Could we get away with fewer? So what this gives us right now, though, is a result that says per node we keep a sketch or logarithmic number of sketches, so in total polylogarithmic amount of space to answer these kind of connectivity questions. And it turns out that that also gets us something quite powerful. So once we have connectivity, we can also get k connectivity. Essentially, we sort of, for a fixed k known in advance, our graph is k connected essentially if we can pull out k independent spanning forests and look at whether that union of spanning forests is k-connected. So what that would mean is we would sort of run that process I just told you through once to generate the first spanning forest, come up with a set of fresh sketches, remove those edges in that spanning forest from the graph, look at the spanning forest of the next graph with those edges removed, and so on. There's another nice reduction that says if we can understand the number of connected components, then we can understand connectivity. Essentially what we do is we do this sort of little trick. We take our graph and we create sort of a new graph with nodes and shadow nodes, so that every edge in the new graph that connects, in the old graph that connects two nodes, is then represented as an edge that connects that node to its partner's shadow and vice versa. And sort of proof by picture, what it says is if this graph is bipartite, then, or rather if this component is bipartite, then this sort of shadow copy ends up with two independent components. But if the graph is not bipartite, then you end up with cross edges that mean that this sort of shadow component is just one component. So how do you use that then? That construction that we saw basically not just told us connectivity information, it told us the full set of connected components. So online, as you see an edge, you can create the sort of the two shadow edges in the transformed graph, plug that into your connectivity sketch structure, and then from that determine the number of connected components and hence determine whether or not your graph is bipartite. its spanning tree. Okay, so that was L0 sampling and its application to graphs. And that's something that's also very active right now, because this is something that presentation came from SOTA 2012, and then since then, sort of independently, similar ideas from Valerie and others have been used to actually solve dynamic graph problems. Not quite in this sort of streaming compact space, but just using that compact data structure as a way to generate a fast algorithm for maintaining connected components dynamically. So that's an interesting example where these kind of randomization ideas have applications outside of sort of small space big data settings. So let me now talk about L2 sampling as a second sort of sampling paradigm. So we're going to go back to frequency moments. So again, we have our vector of frequencies, fi. The kth frequency moment is the sum over all indices I of the ith item raised to the power k. And we're going to suppose that we have a procedure that gives us L2 samples. That is, that samples the ith frequency with probability proportional to fi squared. And additionally, we're going to assume that this gives us a good estimate of fi. And we're going to say, well, what can we build from that? We're going to argue is that actually that estimate, from that sampling procedure, we can build an estimator for frequency moments for k greater than 2. So our estimator for any k greater than 2 is going to be sample an item from this distribution, use its estimated frequency raised to the k minus second power multiplied by f2. So again, we're sort of pulling in a lot of assumptions here. Assume we have a good estimate of f2, good estimate of fi. So from that estimator, what that immediately gives you, just sort of working through, you're sampling the ith item with probability fi squared over f2, multiplying that by f2 to get fi squared, and then multiplying by fi k minus 2. So it's sort of immediate that in expectation gives you the kth frequency moment. So what we're going to try and do is sort of follow that pattern that we saw yesterday of saying, well, let me understand an estimator by looking at its expectation. Its expectation is what we're trying to obtain. Let's understand its variance by looking at how can we bound the variance, and then try and plug this into an estimation framework. So in terms of variance, we're actually doing reasonably well. We just sort of work through the variance calculation, look at the probability, look at the squared estimator, what does that give us, sum it up. What it basically gives us is f2 times f2k minus 2. Well, we don't quite understand what that is. We're trying to shoot for this quantity fk. We've got a variance in terms of f2, fk minus 2. So I have to do a little bit of manipulation on this. I'm not going to go through the details, but basically we want to re-express f2 times fk minus 2 in terms of what we're looking for, fk and the domain size n. What we do is just plug through some sort of standard inequalities to get that this term we can express actually in terms of n to the 1 minus 2 over k and fk squared. Okay, so we just do a little bit of manipulation to turn that expression of the variance into something slightly more convenient.
So, Graham, just to
yes.
clarify, is that bit of analysis the same as an AMS?
I don't think it's the same. So the question is this the same analysis in the AMS paper from '96? It's the same objective. I don't think it's exactly the same route that they follow.
They don't use Helder's inequality, but they.
No, but is it the same inequality?
It's the same inequality.
Oh, okay.
Yeah. So this is the proof just to compress to fit on one slide using this bit of technology. Yeah, I think they sort of did an inductive proof, but you can do it this way too. Okay. So where are we? We're trying to estimate fk via L2 sampling. We have an estimator. It's correcting expectation that has bounded variance, bounded in terms of the square of the quantity we're trying to estimate, and this sort of moderate polynomial in n. So what this says is that if we take a large enough number of repetitions, in particular if you take n to the 1 minus 2 over k times 1 over epsilon squared repetitions, this is going to pull down the variance to epsilon 1 over epsilon squared, sorry, yeah, pull down the variance to epsilon squared times fk squared. And then we can use that recipe we saw yesterday that says we'll just plug in the Cherev inequality. That gives us constant probability of a good estimate. And then, again, plug this into the Chernoff bounds to say if we then take log 1 over delta repetitions and take the median of those repetitions, then we get that constant probability pushed down to delta probability. Okay. So all that says is that we know that once we get to a bounded variance, then we know the steps to take to turn this into an estimator with strong concentration bounds around the desired quantity. So that sort of gives an outline of how this would all work if we could do L2 sampling. So the only trickiness here is to say, well, how are we going to do the L2 sampling? So we're going to design a method for approximate L2 sampling using sketches that we've seen already, show that this gives us about the right distribution and it gives us the right information that we need about the frequencies. I'm going to be a little bit sketchy with the details because we're going to have some relative errors creeping in. I'm going to do the analysis assuming we have exact values and hand wave a bit and say that once you have, all you do is you just sort of add some epsilons into the analysis and it all goes through. So the main trick we need here is this reweighting trick. What we want to do, we want to say, how am I going to sample from this frequency distribution so that I sample proportional to the squared weights of the frequencies. What I have is I have sketches that are going to let me recover information about squared weights of items. But I want to then sort of turn this into a sampling process. So what I'm going to do is sort of remap my input based on random rescaling. So what I do is for every element I, I'm going to pick some random weight ui in the range 0 to 1 and rescale fi by 1 over ui. So this is giving me a new vector g, and I'm going to build a sketch of that vector g and pull information out of that. What's the intuition here? The intuition is that we're going to be looking for large frequencies in the vector g. And what's the chance that some element has a large frequency? Roughly speaking, it has a large frequency. It has a greater chance of having a large frequency if it was large in the original vector f. But even if it's small, there's some small chance that it gets boosted by its random value ui large enough that it will overall be large. So essentially, it's going to push us in that direction of large items having large probability of being sampled, small items having small but non-zero probability of being sampled, and it's going to turn out to be proportional to the square of their weights. So what's the exact process we're going to do? We're going to sketch this vector g and sort of recover the heavy elements of this vector and return element I and its associated estimated weight if there's a unique I in this resampled vector, so that the squared reweighted weight exceeds some threshold t, where that threshold t is f2 of the original vector scaled by 1 over epsilon. Okay. So what's the argument for why this is doing about the right thing? What it's basically saying is, what's the probability that this rescaled squared weight exceeds this threshold and is unique? Well, that we just break using an independence argument into the probability that the squared value exceeds the threshold times the probability that everything else falls below the threshold. This event here we can just rewrite in terms of fi and ui. It's the event that the randomly chosen weight ui is less than epsilon fi squared over f2. So it's saying, what's the probability that a random value in the range 0 to 1 falls below a particular value? Well, that's exactly that value. What's the probability that everything else doesn't cross that threshold? Essentially, that's close enough to 1 that I'm going to hand wave a bit and say we treat this as 1, where we don't lose too much probability mass from that. So it says that the probability that we recover I ends up looking proportional to fi squared over f2 times epsilon. And for this way, that's sort of reasonable. Ideally, we wouldn't want that. Ideally, we want just fi squared over f2. But we're sort of balancing these two pieces. We're balancing the probability that this element does exceed the threshold with the probability that everything else falls below. So what we end up with is actually a relatively small probability that we get anything, because most of the time, almost everything falls below the threshold. But occasionally something sticks its head over the parapet. When we do, we grab it, and that comes across with the right probability. So we only have epsilon probability of recovering anything. When we do recover anything conditioned on that, we're approximately uniform. So we just repeat this enough times that something is likely to get through this sampling procedure. Once we recover this reweighted item, it turns out that because we sort of boosted this item's weight up and effectively smushed down the weight of everything else, actually we have a pretty good estimate of the weight of that item by reweighting by UI. So when you sort of step through, what it means is you actually estimate the squared weight of this item with relatively good error. So we actually get a relative error approximation of that weight. And that's what you plug into the outline that I sort of showed you a few slides back to get your estimate of FK. So as promised, I've dropped a lot of details here, hidden a lot of subtlety. One thing I didn't mention was these UIs. I've treated them as if they're fully independent. Of course, if we're doing this in the whole sketching regime, I shouldn't be treating them as independent, but we're going to skip over that detail. And this sort of derives from the work of Andoni, Krautkramer, and Onak in the precision sampling work. Question?
So, I mean, maybe I'm missing something, but to get the derived stream, the GI, because it's based on the frequency count, it just means that when you look at an item, given the UI, you are more or less likely to actually take it for your derived stream based on the UI value. Is that how you do it?
Okay, yeah. So as a question is about exactly how we're deriving the stream from the original stream. Actually, so we're not sampling into those streams. We are reweighting. So if you think of the original stream arriving, it's describing a vector. We're effectively reweighting that vector everywhere with the UIs. Yeah, yeah. Because so we just. So yeah, think of these just as rescaling, and then because all the sampling work comes sort of after you pull things out of the sketch. Okay. So what does this say? This says that when you put all these details together, we can use L2 sampling actually to give us pretty good bounds for FK estimation. Okay, so that was LP sampling. Let me talk now about matrix computations and then move on to lower bounds. So what's the fundamental question in matrix computation? As we've heard already, the fundamental question is, given two matrices A and B, we want to approximate their matrix product AB. Well, how do we know how well we've done? We want to measure the error in terms, if we're going to come up with some answer C, we're going to measure the terms in terms of some normed error. And mostly for convenience, that norm we're going to pick to be the Frobenius entry-wise norm. That is, we're just going to sum up the squares of the matrix of the entries and then take the square root of that summation. Partly the reason for adopting that is using the technology we have, using sketches. That norm is going to be sort of the most natural one. So I don't want to. I'm going to not spend very much time on matrices, but I just want to sort of think about, given the sketches that we have, what do they tell us about this problem? So what's the first thing you can try? The first thing you can try is to say, well, I could just build a sketch of every row of A and a sketch of every column of B, and estimate the ijth entry of the matrix C by using that inner product of the sketch of the ith row and the bth column. That's an inner product. I know through sketching techniques that estimate will give me additive error in terms of epsilon, the parameter of the sketch, and the product of the two norms of those two vectors. So what that says is just using sketching results, if I do that for every entry and sum over all entries in the matrix, then the squared error is going to look like this summation of epsilon squared times sum over all ij of the squared norm of row I and the squared norm of row j and b. And you plug that out, and what that gives you is a result in terms of Frobenius. So in fact, the Frobenius norm of the error is actually sort of in the form that you want. It's epsilon times Frobenius norm of A times Frobenius norm of B. So that's a little bit lax because I've assumed here that this error bound holds in every case. And actually, I need to sort of reason a little bit more about when that holds. So one way of making that hold is to say, well, let me just sort of pump up the probability for these sketches. Let me just make sure that every sketch gives me this guarantee with sort of polynomially small error rate. That comes fairly cheaply. That just gives me log factors in my sketch size. And then I can argue that this holds everywhere, and I get this result. So that's a little bit unsatisfying because log factors count. And in some way it feels that we shouldn't need that. We shouldn't need that sort of union bound, really, because in some sense we might have some positive errors on one entry, some negative errors on another entry. These things should sort of not add up so adversarially. So in fact what you can do is instead of looking at the error on each entry, bounding that, and then sort of summing those bounds, you can instead write a random variable that's the sum of the errors over all entries, and use the technology we have, just sort of apply a variance Chebyshev bound once. So what that says is sort of just using a single set of sketches, you can look at the overall error of your estimate of the product, show that the variance is bounded in terms of epsilon squared times product of the squared Frobenius norms. And you think, well, that's great. I can follow that recipe that we've seen several times. We use the Chebyshev to get us constant probability. And then we just have to do that median thing with a Chernoff bound and we're done. Well, so there's one problem here. That median thing with the Chernoff bound is fine when you're dealing with a single numeric value because you have an order and you can look at the median of that. But if I have a bunch of estimates of matrix products, and each one I know has a constant probability of being good, how do I sort of throw out the bad ones and focus my attention on the good ones? There isn't really a strong notion of a median of set of matrices. So we have to do some sort of ugly tricks here. What we can do is essentially find an estimate that is in some sense close to most of the others. And if we can find an estimate that's close to most of the others, then you can argue that estimate is therefore a good estimate. So what you do is you sort of estimate what is that overall Frobenius norm and find an estimate that is closer than half that distance to more than half of the rest of the sketches and the rest of the answers, and adopt that as your estimate and argue that actually then with high probability that's a good estimate for the matrix product. So it's a little bit sort of fiddly to do that. You can sort of go other approaches. So this is due to Clarkson and Woodruff. So they sort of outline this approach. They also say that if we amp up the independence of the hash functions in the sketches, then actually you can just use a single estimate with more powerful hash functions and also get that result. Okay. So I wanted to mention that just sort of in the sense that already with sort of sketch techniques, it gets you to a pretty good place for matrix multiplication. And it sort of suggests that of the more advanced techniques we've seen for these kind of problems, again, maybe those have ways that we can think of them in terms of this kind of sketch analysis. So I'm going to skip through some other pieces. so that we can spend a bit of time talking about lower bounds. So I've painted a fairly rosy picture so far. I've said, well, we have these nice techniques. We have a lot of sketch constructions that let us do things that sometimes on first view look magical. They say we can take huge amounts of data, be it a huge vector, a huge graph, or a huge matrix, come up with a summary whose size is sort of independent or only sort of very weakly dependent on the size of the object we're looking at, and nevertheless pull out important information about the connectivity of the graph, the product of the matrices, the norm of the vectors, and so on. So obviously that's not going to work for every kind of computational question. And there are a lot of natural questions where you can argue that any sketch, any summary of your object that you want to give a guarantee for, to say that that thing works for this kind of question, then that sketch actually has to be so large that it doesn't really summarize. It ends up being effectively as large as the object you're trying to summarize. So the way we construct these lower bounds are based on studying communication games and information about objects that's being transferred. Think of the transfer of information as being via the data structure that we build. So we're going to take a bunch of fundamental problems, argue that those will require a large summary, and then show reductions to those problems to show hardness of other things. So here's our communication game. We have our old friends Alice and Bob. Think of sort of laying out the input as a sequence where Alice is going to process some prefix of that input. And at some point, and Alice, while she goes along, is going to have built up some data structure. And at some point in the middle, she's going to hand over the task to Bob. So she's going to communicate the contents of her data structure to Bob. And then Bob is going to continue processing the remainder of the input. So what this is doing is sort of establishing that link between processing the information and building a data structure or a sketch and a communication game between two players. Right. So in particular, we can sort of make the following argument. If we think of Alice's part of the input corresponding to a string x and Bob's part corresponding to a string y, and we can express the computation that we want to achieve, whether it's an exact computation or an approximate computation, as computing some function f of x and y, then if we can argue that in this communication world, computing f of x and y between Alice and Bob has a communication complexity at least omega g of n, then that sort of immediately translates into a space lower bound for that computation of the same magnitude. And it's a one-line proof argument that basically says, well, if that weren't the case, if there was an algorithm that had better space usage, if there was a sketch that was smaller, then we could essentially simulate that algorithm and use that to solve the communication problem. Okay, so quick warm-up and just to sort of check that we're sort of on the same page here. So if Alice has a string x, Bob has a string y, and they just want to test if x equals y, then just by a counting argument, if we can think of this sort of one-way communication protocol that would send a message any smaller than n the number of bits in these strings, then we're going to hit a problem because we're going to have two messages that correspond to different inputs. So there'll be some strings x that generate the same message, which will necessarily cause an error because Bob might have the same string as one of them, and looking at that message, he can't then tell whether Alice has the same string or a different string. Okay, so any deterministic sketch for equality we know has to take linear in n bits, and this is just to sort of remind us that this is the power of randomization, because very early on we saw fingerprinting techniques which allowed us to solve that equality problem under randomization using just a logarithmic number of bits. Okay, so you can use these kind of accounting arguments fairly straightforwardly to talk about deterministic lower bounds, but in general we're going to be interested in randomized lower bounds. So the way that we're going to tackle randomized lower bounds is by taking a collection of essentially canonical problems, showing that those are hard, and then doing reductions to those. So probably one of the couple of canonical problems in communication complexity that's going to be of use to us is the index problem, where Alice's string is a binary string of length n, Bob's input is just a single index into n, and the goal is simply to output the entry of Alice's string indexed by Bob's index. So this is easy if we can have lots of communication between the two players, but if we restrict the communication so that Alice can only send a message to Bob, then immediately this starts looking harder, and after you think about it for a while, you realize actually, yes, this should be a hard problem. Really, Alice has to send information about every possible index because she has no way of knowing which is the one that Bob's interested in. What does that translate to in our setting? What that basically says is if there's a problem we're interested in, where we want to build a sketch or summary of some large amount of information, and you could potentially use that sketch to retrieve information about an arbitrary bit from a long bit string, then the length of that long bit string that you can encode gives you a lower bound for the size of the sketch for that problem. So we'll see some examples of that in a moment. A variation of index says, let me try and make the problem easier for you. So I'm going to tell Bob not only the index to look for, but the suffix of Alice's string after that index. Right? So I'm going to tell you information which is ultimately not helpful, but seems to contain potentially a lot of entropy. But actually we argue that nevertheless, the one-way randomized communication complexity of augmented index is also high, is also linear in n. And again, we're going to use that in reductions to show other hardness results. And the other big problem in this area that comes up again in n is disjointness. So now Alice and Bob both have binary strings of length n, and their goal is to output 1 if there is at least one location where x and y are both 1, otherwise they're going to output 0. And again, this is a nice problem. So in these two problems, we could only tolerate communication from Alice to Bob. This problem remains hard even if Alice and Bob are allowed to sort of have a protracted conversation between each other. They're still going to find it difficult to identify whether there's some location where both strings are both 1, or whether there are no such locations. So firstly, how do we formalize the intuition that these are hard problems? Let me formalize the intuition by giving more intuition and then stopping short of anything close to a full proof. So these problems have been looked at for a while, and currently sort of the cleanest way we know to reason about their hardness is through the lens of a set of techniques known as information complexity, developed over the past 10 or 12 years. So these rely quite a lot on information theory, which I'm going to sort of, again, skip past quickly, and try and get the idea that you know, go back to that problem of index. Alice has this long binary string. Bob is interested in some entry in that string, but Alice doesn't really know which one. So the intuition here is that Alice really has to send some message that conveys information about every single bit of her string. There's not going to be any shortcuts. There's not going to be any ways out of this. Alice has to communicate at least a constant amount of information about every bit of her string. And indeed, we can sort of set this problem up so that the bits of Alice's input, we can really think of them as being independent random bits. So there's not going to be any compression. There's not going to be any sort of clever way of getting around this. Alice will have to send some information, constant amount of information for every bit in the string, which in aggregate means a message proportional to length n of the input string. So apologies for sort of skipping through the technical details, and again, in the interest of making it someone else's problem, I'll refer you to Amit and his excellent tutorial in stock this year on information complexity. So let's now just take it as read that these problems are hard, that we can't get away with small communication protocols for index or for disjointness. How do we use that hardness to show the hardness of other kinds of problems? So let's in fact look at problems related to ones that we've seen already. So we looked at these frequency moments and we talked briefly in passing about f infinity. So f infinity is sort of the limit of the frequency moments. It's basically the highest frequency of items that we see in the input. So what I'll do is sort of show that in some sense answering the f infinity problem, identifying the highest frequency in the input is hard. So I'll do that starting with an instance of disjointness. So I have my instance of disjointness, two strings, x belonging to Alice, y belonging to Bob. The question that they have is there some index where both are 1? In this case, the answer would be yes, because this fourth index is 1 in both strings. So let me turn this into a frequency moments question. So in this case, this transformation is quite simple. So where there's a 1 in Alice's string, I write the index. So there's a 1 at location 1 and 1 at location 3, 4, and 6. And similarly for Bob, I'll do the same transformation. So he has a 1 at location 4, 1 at location 5. Then treat this as the input to this frequency problem. What answers do we get? Basically, we have this nice bijection that if the highest frequency is 2, then it means that there was an index in both Alice's input and Bob's input that was set to 1. Because we see, in this case, we see that the frequency of 4 is 2. So that's our f infinity. So if the f infinity is 2, then there's an intersection. If f infinity is 1 or 0, then these strings are disjoint. So what this says is that if we could distinguish between the case f infinity equals 2 and f infinity is less than 2, then we could answer this disjointness question. Therefore, we need something proportional to, we need space for this sketch proportional to the size of these inputs to be able to answer the f infinity question. And in fact, because it's a sort of a distinction between 2 and 1, even if we could approximate this answer up to constant relative accuracy, we still need to, we'd still effectively solve the disjointness problem. And this is this holds for any randomized construction because the communication problem allows the parties to use randomization. Okay. So what that says is that this particular problem, finding f infinity or even approximating, giving a relative error approximation to f infinity is hard. Let's go a step further and look at more depth about approximation. So here's a simple reduction with index, where essentially we do the same kind of reduction. So Alice's string is the long bit string. We do the same encoding. Encode where are the entries in this string, or non-zero entries in the string. From Bob's index, y, we just directly encode that as an index. And now what we do is we look at the number of distinct elements here. And we do a slightly different game. So first we look at the number of distinct elements based on Alice's string, and then we look at the number of distinct elements taking Alice's encoding with Bob's encoding added in. Because what we want to do is sort of determine, are these things the same or are they different? Right. So the idea is if the index that Bob cares about has a 1 in it, then we've already seen that index in the encoding of Alice's string, so f0 doesn't change. But if it has a 0 in it, then when you add this into the input, then f0 does change. So by looking at those different cases, if we can distinguish those cases, even with approximation, then we can recover that information about that bit. So what it says is if we can approximate f0 with approximation that looks smaller than 1 over the length of Alice's input, then we can solve index, and so we need linear in n bits. Rearranging that, that gives us a first lower bound of 1 over epsilon for the f0 problem. So that's a start. We saw already there was an upper bound of 1 over epsilon squared for this problem. So this lower bound says 1 over epsilon, so it leaves for now the question of whether that true bound should be 1 over epsilon squared or 1 over epsilon. In fact, I think I have to skip the details, but there's a slightly stronger reduction from the gap-Hamming problem that shows, in fact, this lower bound is 1 over epsilon squared. So the algorithms that we have that take space 1 over epsilon squared for estimating the number of distinct elements are, in fact, asymptotically tight in terms of their dependence on epsilon. Okay. I won't say much about other reductions. I want to sort of wrap things up now. So here's a quick high overview of another reduction that we can do to augmented index for that problem of matrix multiplication. So again, we've seen matrix multiplication algorithms that have space proportional to 1 over epsilon squared. Again, could we do better? Could we have a dependency that looked more like 1 over epsilon? What we do is again the same kind of thing we've already seen a few times. We're going to take some input and use it to code up an instance of the problem. So what we do in this case is we take our input to augmented index, where Alice has string x, and make a matrix A that encodes that. So it's going to be a matrix with an initial block of +1s and -1s, where you think of +1 corresponding to a 1, -1 corresponding to a 0. So you can start coding up the string here. Then we're going to have a next block where we do the same thing, but we're now doing it with +2s and -2s. Then a block with +4s and -4s. A block of +2 to the k's and -2 to the k's. So we're sort of coding up our string in these blocks. Then Bob is going to create a matrix that encodes the index that he cares about by sort of working out, well, where has Alice put this bit that I care about? Let's say Alice has put this bit in this column here. Bob will then sort of set up a matrix that's 0 almost everywhere, but that then just reads off this column. So how does augmented index help? So what Bob also does is he uses the fact that he knows the suffix of the string x to say, well, there might be additional blocks afterwards. I can just remove those contributions. So what it means is that the block that I care about, the information that I care about is encoded in a block of highest weight, and I can look at what's the sum of these weights. And essentially the argument goes through to say, well, if Bob can then read off this information about this column via matrix multiplication, and if he can do that without too many errors, without too much additive error on each entry, then he can recover with constant probability what that bit was, whether this corresponded to a +2 to the k or a -2 to the k. And in terms of what that means about the Frobenius norm of these matrices, we can sum those up, rearrange things, and basically argue that if Bob can do that recovery with sufficient accuracy, he can recover that bit, and therefore he could solve the index problem. So how does the augmented index play into this? Sort of plays into it in a slightly interesting way, because essentially if we just had a single instance of the index problem, we would just code this up using this first block of +1s and -1s. So the way that augmented index works is it allows us to sort of do this amplification of weights, because then these dominate everything else and mean you can ignore stuff away from the bit that you're interested in. And so it basically gives you an extra log factor in the lower bound. In other words, if you try to do this reduction using only index, you get a lower bound that's still dependent on 1 over epsilon squared. But when you additionally invoke the power of augmented index, it means you sort of pick up this extra log factor in the lower bound, so you can prove a slightly stronger lower bound. Okay, so I'm going to skip over gap Hamming, entropy and F0, and sort of start to wrap up. So over the course of these two talks, I've basically tried to describe quite a large number of different tools that we have at our disposal. There's actually quite a lot of things that we understand how to do in this setting. We can do vector equality via fingerprints. We can recover entries of vectors via sketching techniques. We can estimate Euclidean norm and inner products. We can look at distinct elements F0. We can approximately recover sets. We can do uniform sampling. We can do L0 sampling, L2 sampling. Using those techniques, we can do graph sketching, frequency moments, and we can sketch matrices. So what I'm trying to communicate here is that we have at our disposal quite a wide range of powerful tools that we can then start sort of putting together and building more things on top of to solve more complex and more detailed problems. At the same time, we also have a bunch of lower bounds that say, you know, there are some problems that we can't solve and shouldn't really expect to solve with a small sketch. Obviously, we can't test equality. We can't recover arbitrary bits from a bit vector, even if some unhelpful suffix of the vector is given. We can't determine whether two n-bit vectors intersect. I didn't talk about gap Hamming, but essentially we can't distinguish the case when there are two vectors, whether they have a small difference in Hamming distance or a slightly larger difference in Hamming distance. And when you use those results, collectively what they give you is the ability to show lower bounds on the size of any summary structure that will let you find the maximum frequency, approximate the number of distinct items, or approximate matrix multiplication. So where is this field of streaming and sketching currently? What are the hot areas? Basically sort of extensions of everywhere that I've just touched on. So obviously sparse representations of high-dimensional objects connecting to the world of compressed sensing is very active, building on techniques extending sketch ideas, and that you can see is the basis of some of the very recent results in areas like sparse fast Fourier transformation. Connecting to the matrix world, again, there's a lot of activity and interest around numerical linear algebra via sketch summarization techniques. So I just mentioned matrix multiplication. All the natural questions make sense in this setting. Can we find K-rank approximations? Can we do linear regression? Can we find representations of PCA SVD eigenvalue decompositions? A lot of activity around graphs right now, spawned by the recent results in that area. So I talked about connectivity and how that gets you things like K connectivity by partightness. Lots of other graph questions where results are starting to emerge. You know, can we find a sparse representation of a graph effectively from a sketch representation? Can we understand how to do clustering within a graph? Can we find matchings within the graph, again, via sketch representations? I think I said about one sentence about geometry, but actually geometric questions are very natural within the context of big data. We want to find sort of compact representations of large number of points, solve various optimization problems like facility location. That then connects through to geometric interpretations of machine learning. And lastly, you know, again, I sort of mentioned briefly one of the attractions of building summaries that have these kind of flexibilities is that they very naturally distribute. So most of the techniques I told you about sort of distribute in a sort of a trivial sense, that you can just build a sketch on your chunk of the data, I can build a sketch on my chunk of the data, and we can naturally combine those sketches via some simple addition process. So the next question is, well, how do we do something more interesting with these? How do we incorporate these into particular models of large-scale distributed computation? MapReduce is sort of the best known such model, and there's been some efforts around incorporating sketch computationals there. But there's also ongoing work around, so MapReduce is essentially sort of a batch computation. It says, I have my fixed input, I want to do this large-scale computation over 1,000 machines to get a particular output. There are also continuous variations. We want to say, as the input varies, as we get more input arriving, how do we continually track the answer to some function, some question over that distributed data? Okay, so let me end now with another advertisement for Andrew's upcoming course on streams, starting very soon now. Book seats early to avoid disappointment. And the workshop in a week and a half's time on succinct data representations right here. Okay, thank you. Any more questions? Okay. Coffee, thanks.